Okay, so they give you this picture. The next figure could provide practice in addition, subtraction. The figure is completed by filling the upper two circles with the sum obtained by adding diagonal. Okay, so the example they give you is 9384. Don't ask me why they don't have a circle off the other side. So 4 plus 9 is 13. 8 plus 3 is 11. And then, yeah, circle to the lower right is filled in one of two ways. Adding the numbers in the upper circles, adding across the rows, adding down the columns, and then adding the blah, 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 blah. Okay. So if I add these two, I get 24, right? But if I also add across the rows and add down the columns and then add the results, 9 plus 3 is 12. 8 plus 4 is 12. 12 plus 12 is 24, right? Funkadelic, yes? Okay. Let me see. What more can I say here? Yeah, so what? Okay, so I don't know. One of the questions, hopefully, is why does this work? Let me see if they do that. I don't know. So why do you think this works? So what is this number made up of? How did I get 11? 8 plus 3, right? And of course 24, one way I got it was just adding these two together, correct? How did I get 13? 4 plus 9, 11. So if I add those, of course I get, no I don't. I get 24, 11 and 13. How did I get these two? 9 plus 3. So if I put 9 and 3 together, there are two properties I'm using. Are you guys all with me? So here's the original way I got 24. I just added the numbers in the circles. Cool? The other way you can get 24 is adding across and then adding those up, or adding down and then adding those up. So we'll do that one next. So I got that 12, that first 12 by 9 plus 3. What two properties do I need to use to be able to put the 9 and 3 together? Okay, one of them is commutative. I got parentheses involved, associative, right? You guys understand? Is that cool?
Yeah, I think when I look back at it, like,
Does that sound better?
a little.
It's weird because it's something. It's not like something you see every day, right? And they don't do the best job explaining. They don't do a bad job, but they don't do the best job. And what do they ask you to do? Oh, then they give you some other problems, and they say fill in the stuff. Okay, is that? You think it's better? You at least have a way to attack it now.
Yeah, I mean, I figured out A and B just fine. I just remember struggling with C.
All right, C. Use variables to show why this. Oh, yeah. Okay. So the way you can do that is you can create. There's only 4 examples. X, Y, Z, W, right? So this is the use a variable approach. So it shouldn't matter what numbers I put in there. This should always come out the same because it's built off of properties, and those properties work for all whole numbers, correct? That's the idea of the property of whole numbers. So if I make the variables and they represent every possible whole number, and I do the exact same process, you can then kind of see why it would be true. You can use the properties directly. Does that make more sense? Okay, I like it. I like it. Some classes I use free textbooks. There's not a lot of textbooks that kind of work for this kind of class. And the ones that I found are, this one's not the greatest either, trust me, but when a free textbook doesn't quite explain something well, you can sort of let it go a little bit. This one's not exactly free, so you're like, come on, people. All right. Anything else from homework stuff or general stuff? Yes?
You gave me my quiz back on Tuesday, and can I turn it in now?
Hell yeah. Hell yeah. Okay. Yes?
Can you explain
Thank you.
question 5? I'm just confused what it's asking.
Set B 5A. Oh, okay. So first question is, if I ask you, for example, can you guys do this right now? What is 6 base 7 plus 2 base 7? Can you guys figure out what that is? And you can actually use some of the addition, the thinking strategies associated with addition.
11 base 7.
Why do you say that?
6 plus 2 is 8.
And then you kind of convert it. What's the way you can stay in base 7? What would 6 base 7 plus 1 base 7 be? 10 in base 7, correct? And then, but I'm adding 2. So one thinking strategy is to break this up as 1 base 7 plus 1 base 7. And then use associative property, blah, 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 right? Did you guys see this? Is that cool? And then this is 10 plus 1, 11 base 7. So you can actually stay fully in the base. And it feels like it should be easy, but it's frickin' base 7. That's not, thankfully we have more than 7 fingers, so that's not something we're used to using. So that's why it's not like easy, but it's not as hard as it first seems. Now, this question specifically says, something about this room, it's amazing. It's weird. All right. This specific, which one was it again? 9? No. 5. So close, Jeff. Yeah, so on that one, you just have to actually show that that's true, that the equality holds. So it's kind of a little bit silly. And by using a different number line for E. Oh, okay, so they want you to actually use a number line. So what's neat is, how would you make a number line for base 5? 0, 1, 2, 3, 4. So we're in base 5, right? 0, 1, 2, 3, 4. I think I heard it. 10, yes. And I always want somebody to walk in right then and be like, wrong room, but what the hell are you people doing? So if I'm going to add, good Lord, what comes after this? 11, 12. Good Lord. It's been a good life. I, of course, left my water back in my office. I'm going to go run and get it in a minute. Let's see now. If I talk like this, so I'm going to add 3 base 4 to 3 base 5 to 4 base 5, right? For example. I could do it the measurement model, remember? There's 3 base 4. And then how do I do 4 base 4? Don't I just go 1, 2, 3, 4? So 3 base 5 plus 4 base 5 looks to be what? 12 base 5. And let's check it. 4 base 5 plus 1 base 5 is what? 10. Kick ass. 10 base 5. You with me? So 4 base 5 plus 1 base 5 is 10, and then I have extra 2. Does everybody see that? Sweet. It's exactly the way our number system works. We're just a lot more used to it. But this, of course, like I said, this is the measurement model of addition, right? Okay. So that's what they mean by using a different number line for each base, right? So our number line would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I had base 2, it'd be 0, 1, 10, 11, 20, 1, 0, 0, 100, right? It'd be crazy. Is that? Okay. Maybe. So those different bases aren't really going to go away fully. We're not like done with them. They're going to keep coming back. Okay. Anything else from homework stuff? Okay. So real quick review of what we did last time, and then I want to show you a few videos of some students working some stuff out, and then I'm going to show you kind of a silly video that I share with my fellow math teachers. We'll see what you guys think. You're all like, this sounds great. This is some math teacher's opinion of what's silly. Great, fantastic, show us. So last time we talked about addition of whole numbers, so we talked about properties, we talked about strategies to actually do them, right? Should I give this to you yet? No, I'm not going to give it to you yet. We then talked about subtraction approaches, right? So with addition, you could use set method. So if you wanted to do 3 plus 4, you could have a set of 3 things plus a set of 4 things and actually show that they make a set of 7 things, right? And that's the very natural way for students to first do it. If I said 3 plus 4, they would take 3 blocks, then they would count 4 blocks, and then they would count and go 7. Yay, right? That's a natural thing, and that's just a on-paper representation of that approach. Cool, I like it. Then we talked about the measurement model of addition. We just saw an example of that in base 5. We talked about subtraction. Does anyone remember different approaches for subtraction? There are some different models, different kind of approaches. Takeaway, that's your classic, right? I had 10 marbles and Billy stole 8. Billy. So now I got 2, damn it. Yes.
And then the missing addend.
Missing addend. Kick ass. That would mean that would be something like, I've got 8 marbles, Billy's got 11. How many more marbles do I need until I have the same as Billy? That's still a subtraction problem. So I really want you to understand, we kind of inherently totally get that those are completely different kind of problems, but they all come back to the same math. Does that make sense? That's not something you're just born with knowing, right? Sorry, I cut something. Yeah.
Isn't there also the measurement?
Yeah, within those two, there's the set method and the measurement, set model and the measurement model. So those 2 overarching approaches could be modeled with those 2 things. I like it. And then, of course, there was the comparison. I think it's one of the last ones we did. That's more like what I just said, but comparison could be either takeaway or missing addend. So comparison is just like I just said. I'm comparing myself to somebody else. How much money do I have? How much money do you have, right? And comparing how much more what I need to make to have the same amount of money. That would be a comparison, but that would be a missing addend comparison. Okay, are you guys sort of with me? All right. Okay. So what I want to do, I think we also did. Yeah, we did. Did we? No, we're about to do that. So we did addition, subtraction. So I want to show you a few videos of some kids working some problems out. You're going to see some familiar 3-2. Which also, incredible enough, is where we start doing multiplication and division. So we're going to see a lot of the same kind of approaches to things. So there's going to be the set model method, and there's going to be the measurement model. There's going to be kind of similar things. We're going to talk about properties and such. Let me ask you this question. What is the most fundamental definition of multiplication? Does anyone have an idea what that might be? Think way back to, like, if I ask somebody what 3 times 4 is, what do you think the most immediate, basic way to figure out what that is would be?
When I work with kids, they just add 4 like 3 times.
Yes! So, take what you said, make it a 2-word phrase. It would be repeated addition. Kick ass. And this is part of what Common Core shows and why, for example, 4 times 3 specifically is 4 groups of 3. You agree? Okay. So 3 times 4, even though it has the same answer, it would be represented by a different physical reality. Does that make sense? Okay. So if 4 times 3, so to do the set method, the set model, I should say. How could I do the set model? I would need 4 groups of 3. So I would just, whatever your favorite shape of the day is, I just need 4 groups of 3. Weehaw. Okay. And you can count them up and you can see what that is. So I've seen some Facebook posts. Facebook is basically for old people to go on and yell about stuff. And on Facebook is the worst. I don't go on there very often, thank the gods, because every now and again I'll see a order operations problem that everybody is arguing about, and I just sort of like silently weep to myself, and okay, all right. So they get upset when a student does 4 times 3, but they do it the way you should do 3 times 4. I mean, so on one level, parents will see that the answer is the same, and they're like, why are you teaching my kid? Because the concept needs to be fully explored before we can connect the two things, correct? So 4 groups of 3, 3 groups of 4. It's not obvious those are the same. It isn't. To us it is, because we know all the shit, right? So somebody who's just learning everything, that's not obvious. So we need to explore those and then connect them later. So what would 3 times 4 look like? 3 groups of 4 is crazy. Now, again, to us, to most adults, that would be like, why are you doing this? It's just 12. What are you people doing? What are you doing to my kid? Just tell him it's 12. It's like, no, no, that's not how anything works. So, okay, just to kind of, blah, 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 and then, okay, all right. Did I count? Yes, I counted. Okay. There's also measurement model. So there's a few different ways to look at measurement model, but fundamentally it involves a what? Number line. That's the most fundamental use of measurement. We'll see that kind of extended today a bit. How can I use measurement model to do 4 times 3?
You put 4 lengths of 3 end to end.
Yeah, so you need 4 steps of 3 is another way to kind of think of it, right? So normally when I have a number line, I talk about stepping around the number line. So 1 step of 3, 2 steps of 3, 3 steps of 3, 4 steps of 3, and you get to 12, okay, right? And of course you can imagine if it was 3 times 4, it would be 3 steps of 4, and you still end up at 12. Are you guys all with me? Does that make sense? So this again is the measurement model. Okay. What's gonna suck is the word measurement is used in a slightly different way in this section, so we're just gonna deal with it. So let me kind of put down a definition of what it is we're doing. Do you work better? Yes. Okay. Good. Has everybody got that? Okay. Good Lord. How old is this thing? All right. So a definition of A times B involving some. Holy crap! None of my markers. All my markers are dying. So A times B, what is the official name of times? The result of a multiplication is the what? Product, kick-ass. So this is a product. Well, not produce. What do you call the individual members that go into creating a product? For example, give me 2 numbers that multiply 18. Factors. Cool. You guys see immediately. I love it. So these are just called factors. Okay. Of course, at the level that most of you will be teaching at, what symbol do they normally use for multiplication? Yeah. And of course, I could also just put them together. So you got the dot, you got the X for times, and then you can just put them together, right? Now, of course, that leads to a very weird mistake, which is if I tell a student what's 5 times 3 and they write that, that's a problem, correct? Okay, I like it. Yes?
Why don't we just use the dot for all multiplication? Like NB or that I understand, but why use the X to this? Doesn't that just confuse them later? Because it confused me. because I was like, why are we using an X if it's dot?
If it were up to me, we would teach algebraic concepts way earlier, and I don't mean like full algebra. I just mean X, sort of like missing add end. I could put an X in the place of what I don't know what it is, just to introduce that idea. So they're more used to algebra, which is one reason why we stopped using the X at some point, because we're like, otherwise in algebra that would be A times X times B, correct? So if it were up to me, we wouldn't. It's sort of historical, and there's also other reasons related to, some of you guys know this, but these symbols actually, this is actually used in higher mathematics to mean a type of multiplication. I don't know if anybody, I know at least one of you do, but they're called dot product and cross product. We do not need to know them. You with me? You don't need to know them. But it's something that it's kind of sad to me that there's so much more behind these symbols, and it comes back. So for a while ago, we can't use that anymore because it means X, and then it comes back because now it means some other different kind of multiplication. Anyway, you don't have to know it, but bottom line, I agree. I wish we would just use dot for everything, but the dot, one thing about the dot, especially with little kids, it'll get lost. X, they can make that shit, and it's not gonna go in, they can see it. You with me? But a little dot dude, it's gonna get lost. Does that make sense? So that is one argument for using at least some kind of a bigger symbol, and X is just already traditionally meaning multiplication. Yeah. All right, I love it, I love it. And by the way, I mean, I hope a few of you guys, there are, in some of your other education courses, you're gonna be reading books about all these various things, which is great. You're gonna read about stuff. I really hope that some of you guys take a little interest in like a little bit of a history of mathematics, because I would love to teach a history math course, because like, for example, I'm not gonna suddenly do it, the square root symbol, why does it look the way it does? Did it have to be that way? Why do we put exponents where we do? Did we have to? Do you understand what I'm saying? These are little things you could pepper into your conversations with students to make them aware that this shit was made up by us. And they are one of us, so learn how we put this stuff together. It didn't have to be this way, which is, again, one of the reasons why we do Mayan and Babylonian, just to show you the entire number system didn't have to be the way it is. Okay, I'll stop. I'm sorry. Okay, what else can I squeeze out of this? I forget. Oh, yeah. So going back to the definition, I'm going to very often I'm going to do dot, or I'm going to do parentheses, right? So I think most of the time I'm probably going to just do a dot. That would mean B plus B plus B how many times? A times, right? That's the basic definition. And again, that's the most fundamental definition of multiplication, is repeated addition. Right? What's the most fundamental multiplication problem? I have 2 apples in every crate, and I have 5 crates. How many apples total do I have? 2 plus 2 plus 2. Repeated addition, and then they start to make shortcuts, and then they understand that's multiplication, right? I love it, I love it. So this would be A, let me bring back an old, new word, right? There's A addends involved in that addition. So what would B times A be? A plus A plus A, we have B addends. And this is involved in a lot of the misunderstanding of parents about why something's marked wrong on an assignment when it ends up with the right answer. It's because the answer is not the most important thing. It's the concept behind what we're doing. You guys kind of with me? Okay. But it's understandable why people don't get that, because they can't think low enough to realize what a student needs to get to where they are. Okay. I have a shirt that says I go off on tangents, and I do. There's a new kind of way to do this than we had with addition, and it's kind of, I'm using this word a lot today, but it's one of the most fundamental picture ways to do multiplication. I'll start with this, because this is what I'm talking about. Right? This means multiplication. Right? If I had this big ass ice cube tray, and I want to know how many total ice cubes there are, well, how many ice cubes are this way? 4. And how many ice cubes are this way? 3. So how many total ice cubes are there? 12. So you could look at it as 4 groups of 3, or you could look at it as 3 groups of 4, right? You guys kind of with me? So you could show why 4 times 3 equals 3 times 4 by just, see if you can do it, Jeff. There you go, buddy. Yeah. Okay. That's 12. That's 12. A student can count. They could do it breaking it up, and they could see, oh, it's the same. And you can start to develop the idea of commutativity. Okay, I like it. Okay. And then, so this is actually, believe it or not, help me out, measurement model. What is it? Basically, it's a number line, right? Don't we have 2 kind of dimensions we're dealing with now? So what's an extension to the x-axis would be the y-axis. This is still measurement model. Isn't it looking more like graph paper now? That's why it's still measurement model. Measurement model is built off of number lines. Here I've just got 2 directions I want to go, so I need 2 number lines. Does that make any sense? I want you to really understand why this is still considered a measurement model. So, how would you do the set model for this? Same problem, 4 times 3. I already did it, I believe, right? But broadly, this is actually called a rectangular array. So if we were a little more, so obviously, does that make sense? It's a rectangular array. I could do a set model rectangular array, which would be something like, so instead of looking at the tray, I'm looking at the cubes, the ice cubes themselves. Does that make sense? So I take the tray and I plop, and there it is on the table. That is now a set model in a rectangular array. Is it important that you know all the combinations of all these things? No. If I say rectangular array, you should be able to create one. If I say make a set model, you should be able to create one, right? Okay, maybe. Does somebody remember we defined multiplication earlier somehow, involving something about sets, and this is bringing back the whole idea of the intersection has to be empty and all that kind of stuff. So remember, we had an idea of multiplication already. I don't know if you guys remember. This is something product. Cartesian product, I love it. If I ask you guys, did I tell you René Descartes? Did we talk about René Descartes at all? Did I tell you about the urban legend about René Descartes? And it's nothing exciting. You wouldn't make a movie out of this. But supposedly he was laying sick in his bed, watching a fly on a ceiling. And he was thinking to himself, I could identify the location of the fly using X and Y. So supposedly that's how he came up with the idea of the XY coordinate system. So he's the one who created our XY coordinate system, which is called the Cartesian plane, right? Cartesian coordinate system. Anyway. Anyone remember what the hell this was? It's okay if the answer is no. So let me give you 2 sets. So if I have A equals, what do you got, Jeff? It doesn't matter. Triangle box, and I got B equals L, W, Z. Does anyone remember what A cross B would be? Yeah, so it'd be triangle L, triangle W, triangle Z, yes? And? Square L, square W, square Z. Is everybody good with that? Do you see how the minute I write that, doesn't it look like it's a rectangular array, right? So remember, this is the number in A and the number in B. If I multiply them together, I get the number that's in A times B. A cross B, across the Cartesian product, I'll just say it like that. Is that okay so far? Do you guys remember that? You just kind of construct all the points you can with the elements of both sets. That's all Cartesian product meant. And you can see, as long as these, well now in this case it doesn't have to be empty intersection. We just make everything we could. It's always going to come out to be the straight up multiplication of the two sizes. Okay. So there's another definition of multiplication we used before. Blah, blah, blah. Oh, here's another way to do this. There's a model we use a lot in probability, and it's called a tree diagram. And you can use it to kind of illustrate multiplication also. Well, shoot and a half. That was way over there. Anybody ever seen a tree diagram before? Not, or somebody think maybe they did, and they're not certain. Okay. A lot of probability classes, you could very often see a tree diagram. So what this is, for example, to construct those, didn't you pick one of these two symbols to start with? So the first branch would be the first pick we have. So I could branch off and I could pick a triangle, or I could branch off and I could pick a square, correct? Off of each of those, I have some twigs coming off. Once I pick a triangle, what could I pick next? LWZ, I like it. And of course, once I pick a square, I could pick LWZ. How many total twigs do we end up with? 2 times 3 is 6. It's another illustration of multiplication. And do you guys see how that's really just repeated addition? Okay, maybe, okay. So I did 2 groups of 3, that makes 6. So I repeated addition. Okay, I like it. Maybe, okay. So that again, that's something you might see. We used it a lot in probability because probability is all about what's the total number of things I could end up with. So I don't know if you guys have ever heard, if there were 13 available toppings for a pizza, the total number of different pizzas you could create is in the millions, which really freaks people out when you hear that. You're like, only, I think it's 13 toppings leads to 7 million. I can't remember exactly what the numbers were. But we're just not used to understanding how many different combinations there are amongst things. Anyway, okay, I'll stop. Okay, so let me see if you guys can remember what are some properties we talked about before of addition, for example. What was the, there's one that was probably new to everybody. The ones you had already heard of were what properties? We already talked about them earlier. Commutative, associative, and then there was one, then there were a couple other ones, but there was one that we started with. That one came later. Say again? Closure, kick ass. So, let me ask you like this. Is multiplication closed over the whole numbers? So what does it take in order to be closed over a set? So I want to make this really, really clear. In order for an operation to be closed on a set, if I take any, go ahead.
Is that it equals a whole number?
Whatever the set is. So if the set is all whole numbers, if I take any 2 elements of that set and apply the operation, I have to remain in the set. So that's why, for example, subtraction was not closed over the whole numbers. Can somebody give me one example as to why not? Subtraction is not closed under the whole numbers. 7 minus 9. So that's 2 elements in the whole numbers, but their subtraction, I'd have to go outside the set to find the answer. That's why I love the name closed, right? It's closed under something. So it's closure. You stay in that house. You don't have to go somewhere else. So is multiplication closed under the whole numbers? Are the whole numbers closed under multiplication? Let me say it the right way. What do you guys think? Can you take any 2 whole numbers and multiply and not get a whole number back? Of course not. Any 2 whole numbers I multiply, I'm going to get a whole number back, right? Okay, so it is closed. So whole numbers closed under multiplication. And of course, we got the old ones, the commutativity. I already showed you a way to illustrate this. I can illustrate my fantastic spelling skills. Anyone remember the thing we just did earlier to illustrate why 3 times 4 equals 4 times 3? You could use a certain model to show a student why that's true. Right, we did the rectangular array, so 4 times 3 is the same thing as 3 times 4. They can count it, they can see it's true. You guys with me? And again, when you do a specific example, that's not a proof. That's just getting a feel for why it might be true. So yes, whole numbers are are commuted under multiplication. I like it. Are they closed under division? Just to kind of look ahead of it. Try it. Give me 2 whole numbers. Any 2 whole numbers.
12 and 2.
Say again?
12 and 2.
12 and 2. What's 12 divided by 2? And what's 2 divided by 12? See, already you can tell they are not, it's not commutative. The idea of commutativity is if I turn the elements around with the same operation in the middle, I should get the same result, right? So 2 times 12 is the same as 12 times 2, but division, no. By the way, real quick, just to kind of blow your minds, you should all kind of know this. There is no subtraction. And there is no division. Those don't exist. And you're like, who the hell are you, dude? Look at my calculator. I see 4 buttons, dude, all right? What are you talking about? So why is there no subtraction? Because subtraction is just adding the inverse. Are you with me? You guys know what I'm saying? And again, on one level, I'm about to say something. On one level, what I'm saying right now doesn't matter. And you're like, dude. But it is interesting to realize that. So like when students have to divide 3/4 by 2, just to go ahead a little bit, and some of you guys I know, we get into the fractions and we're going to focus on that a little bit. They're really confused, but if they just realize there is no division, it's just multiplication by 1/2. And then that's easy, just multiply straight across for that. Okay. Then of course we have associativity. And it's definitely closed under, I'm sorry, I keep saying closed. It definitely has the associative property, right? So the way you would illustrate that is 2 times 4 times 3 has to be the same as 2 times 4 times 3. Now let me take a minute. Can anybody come up with a way to illustrate that visually? And I always want like a smart ass to go, well, that is visual, Jeff. But you know, like a set and that model or something, right? Is there a way to model that? We did commutativity earlier, correct? We could model that visually. I want to let you guys think about it for a moment. Is there a way to model that specific statement? You got a way?
Couldn't you just do like 4 groups of 3?
Good, okay. So looking at this side. So this would be 4 groups of 3. All right, why did I pick these numbers? I don't know. Let me just do this there. That'll be cool. 1, 2, 3. I'll cross bones. Okay?
And then do it one more time.
One more time. So I have double this, right? 1, 2. 1, 1, 1, 2. Okay. And then 2 times 4 times 3 would of course be specific. What would it be? What does this mean? This means 4 groups of 3. This means 2 groups of 4. So I want 2 groups of 4, but then I want to do that 3 times. Shit. And then a student can count, blah, 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 and they can see that it's the same answer. Is that cool? So this is going to be, if you manage to be lucky enough to teach a very low grade, your everyday life is going to be, how can I illustrate this concept with something they could hold, something they could draw, something, right? Which is kind of cool. And you have these standard manipulatives you can use, you have these stuff. But it's kind of cool to like incorporate stuff the kids bring in or incorporate stuff that they talk about or whatever, right? So that's going to be a huge part of your daily life is being creative with the mathematics. Okay. Oh, there's another property of multiplication that involves addition, and it's not the repeated addition idea. And I really want to make sure you understand why this is true. I forgot what number I'm on. It's the distributive property. And what does that one mean? What's distributive property? Does anyone know? Can somebody give me a problem that would involve distributive property? Yes?
I'm sure this is going to be like 2 parentheses 3 plus 4.
Good. So very often we talk about distribution of multiplication over addition. So let me be very specific. Of multiplication over addition. And I'm going to show you an example in a minute of a situation where it isn't that, but it's still distribution. So the classic distribution we all should know is that. So order operations would say to do what first? 3 plus 4, you get 7, you double, you get 14, right? What would distribution say you're allowed to do? Yeah, so I remember back in the day when I was actually able to teach Math 88. It was one of my favorite classes to teach. A lot of my colleagues looked at me really weird, but I just love, because then it's all about how to explain this. Because you know these students have heard all that shit so many times. They're in college taking Math 88, which is again, 2 minus 3. Talking about what that is. So then you have to come up with all these things that you're like, maybe you haven't heard this, maybe you haven't heard this. A student would say, all right, you told us PEMDAS. You had us remember, please excuse my dumb ass son, or dear Aunt Sally, or deficient algebra skills, or whatever. And you made a big deal out of it, and then right here you're going to tell me I don't have to worry about it anymore, right? So wouldn't a student possibly be kind of upset about that? Do you guys get that? And I've had that happen to me in that Math 88. They're like, wait a minute. You made this huge deal about PEMDAS, and you did the whole thing, and then you're telling me I don't have to worry about it. Are you guys understanding? So why does distribution work? Why does it work? Why am I allowed to do this? And it comes out to be the same number. Why is that allowed? What does this mean? What does 2 times 3 mean, fundamentally? Going back to the fundamental idea of multiplication. What does 2 times 3 mean? What does that mean? I have 2 groups of 3. So I have 2 3s, right? So this is 3 plus 3. Same thing, yes? Okay, so what do I have 2 of now? 2 3 plus 4s. Yeah. Is that cool? That is the definition of multiplication. And now, what's the only operation in the whole damn thing? Addition. And I can add whatever the shit order I want to. That's what associativity and commutativity together mean. They just mean you can add stuff whatever order you want to, dude. So then I could just move shit around, and then don't I get, if I use commutativity and associativity, don't I get 3 plus 3? So I get 2 3s. And don't I get 4 plus 4? So I get 2 4s. So then we said, why do all that shit? Why not just double both and then put them together? Right? It's a little shortcut. So distribution is a shortcut. That's what it is. Are you guys all similar? Okay. All right, all right. Okay. So now we come up to a number that always gives us trouble. So negatives find a way to give us trouble. What's the major number that gives us the most problems? I don't know if you guys, what gives us the most trouble? Anybody know the number that gives us the most trouble? Okay, let me see. What is 6 divided by 0? Neato. So, it's kind of cool. Go with me for a minute. I'm going to ask a really easy question, and I'm going to overanalyze it a little bit. What is 12 divided by 2? That's amazing. I like the way you're all like, there's a trick. Why is 12 divided by 2 6? Now later this semester we're going to talk about division and algorithms and screw all that. Just tell me, why is 12 divided by 2 6? What's the quickest way you can explain to me why 12 divided by 2 is 6? 2 times 6 is 12. Not what you said, but I took the next step. Is that cool? So if 12 divided by 2 is 6, that means that 2 times 6 is 12. Yes? What would the answer here have to be able to do? If I put a number here, that means that that number, when I multiply it by 0, I get... So 2 times 6 is 12. That's why this is true. 0 times some number would have to equal 6. You guys all with me? I mean, that's the idea, correct? Is there a number defined to do that? Do we have any number defined to be 6 when I multiply it by 0? Every number when I multiply by 0, I get. So do we have a number defined to do that? So we call this freaking undefined. Does that sound familiar, right? When you divide by 0, some teachers would say you get infinity. You would call it infinite. I don't know if anybody ever did that with you guys. Or they would call it undefined. Right? I'm sure you guys have seen the word undefined. Did anyone ever explain to you why we call it undefined? That's it. There's no number to define to do what that wants me to do. So you're out of luck. All right, I like it. Okay, kick ass. So that's a little thing, and that kind of goes to this really, really beautiful little property, the multiplication property of 0, which is a times 0 equals 0. It's incredible. So a times 0 is 0, which kind of means a divided by 0 has to be what? Undefined, like we just said, right? And a really good question I'm not going to spend a lot of time on is, what is 0 divided by 0? All I'll say about that is this. That is worse than undefined. That is something we call indeterminate. And that's all I'm going to say about it. All right, so 0 divided by 0 is even worse somehow. Right? It's not 1. It can't be 1. Because what's 0 divided by anything? 0, right? And anything divided by 0 is like infinite. And real quick, why can I say that? Normally you'd say undefined. What is 10 divided by 2? 5. What's 10 divided by 1? 10. What's 10 divided by 0.1? 100. 10 divided by 0.01 is 1,000. What's happening? Let me do this. Just go with me for a minute. I'm sorry. This will happen. We'll have stuff like this, and then Jeff is going to do what he's doing right now. 10 divided by 2 is 5. 10 divided by 1 is 10. 10 divided by 0.1, look at the quick way to do this. I know I'm doing fractions and decimals and shit, but if I just move this over once and I move that over once, 100. So 10 divided by 0.01, if I move it over twice, that's 1,000. Are you guys with me? What's happening to the result as I divide by smaller and smaller numbers? The result's getting freaking bigger and bigger. So the closer I get to 0, the closer the result, well, I can't really say closer, the more the result gets bigger and bigger. So we say 10 divided by 0 is basically infinity. Maybe? Okay. I'll stop. I'm sorry. Okay. So there's a lot of stuff about 0. 0 is just one of those numbers that are weird. And again, we talked about this. You guys know this now. There are entire civilizations that didn't have a symbol for 0. There's entire civilizations that didn't have a concept of 0 because they didn't need one in everyday life, right? Okay. So 0 is weird. Oh yeah. We've seen this kind of thing before, but I want to point it out. I don't know how many of you guys have your book, but page 106. Instead of me trying to, oh my God, trying to draw this thing, I'll just take it out of the book. So remember this thing from earlier? It was for the addition, basically an addition table. So now we have a multiplication table. The big blue part is recognizing the fact that if I know what 2 times 4 is, I know what 4 times 2 is, right? So if I can figure out this part, this lower part here, I automatically know this other part. That's what that means. Then of course, we've got the idea of multiplication by 0, the idea of multiplication by 1. The idea of multiplication by 2 is something we talked about with the addition table a while back, just doubling something. Adding something to itself just doubles it. So now we have a direct doubling happening, right? Are you guys all with me? Somewhat, okay. And then, so there's multiplication by 2. And then you've got multiplication by 5, because counting by 5s is easy. Would everybody agree? Because counting by 5s, you just alternate between 5, 0, 5, 0, right? 5, 10, 15, 20. That's a lot easier. Can everybody count by 7s? Could you count by 7s as quickly as you can, but counting by 5s? Not quite, right? Okay. So you got a little chant for 5, so you can normally get students to really understand the 5s tables pretty quickly. This is interesting. Okay, I don't want to. You can read this if you want to, and this is a little bit strange that they put this here. Later this semester, let me just give you a little taste of this. Does everybody in here realize, fewer and fewer people know this? Do you all know that, how to tell if a number is divisible by 9? If I give you any number, you could do something really quickly and know if it's divisible by 9. And I don't mean put it in the calculator and see. Yes?
You add the number, and then it should, what it is by 10. Like, it should make like.
Okay, it's related to adding the digits.
You add the first and second, and if they make 9 instead.
No. You add
all the digits.
every digit.
No.
And if the result is a multiple of 9, you're golden. So for example, what is 9 times 7? What's 6 plus 3?
9.
What's 9 times 11? What's 9 plus 9? Is that a multiple of 9? Yes. Got a calculator? Anybody? Somebody do 9 times 1,549. Sure.
13,940.
1, 3, what?
941.
What's 1 plus 3?
4.
Plus 9? Plus 4? Plus 1? Multiple of 9. So I could give you just a string of freaking number, this huge freaking thing, and I say, is this divisible by 9? And you're like, you didn't let me use my calculator the other day. Well, you just add all the digits and see if they're a multiple of 9. That's insane. Later, we're going to get a little bit in. I'm going to save most of this for later. But let me give you one more. Does anyone know how to tell us? Now, everybody knows how to tell if something's divisible by 2. It's freaking even thing. 3's got a very similar thing to 9, so I'm not going to tell about 3. What about 4? How can I tell if something's divisible by 4 by just looking at it? What's 4 times 25? So doesn't 4 go into 112? Because it goes to 112, right? Doesn't 4 go into 1200 because 4 goes into 100? Yes? You guys with me? You guys kind of with me? 4 goes into 1100 because 4 goes into every 100. Does that make sense? So extend that idea, and if I give you some big ass number, 89747093652297448. Look at the last 2 digits. I can't say the word digits. Not sure what I'm drinking. The last 2 digits, what are they? 48. Are they divisible by 4? So the whole damn thing is. Is that kind of cool? Has anyone ever heard that before? Does somebody think maybe they did and they forgot? Or do you think you've never heard that before? Because I've noticed over time, real quick, over time, people coming out of high school, I used to have everybody knew at least the 9. Everybody just knew the 9. And then suddenly, less and less and less people knew the 9 thing. And I'm like, what the hell is happening? Right? And that was when a big shift was made to, well, a lot of this can be done with a calculator, so we're not going to do such silly memorization. No, that's understanding our number system. And if I was a student who never was told that, I would be upset. I'm like, shit, tell me that shit. That's useful. Anyway, so there's a future section. We'll talk about every number, even past 9. Obviously 10, I think that's maybe a little easy. We'll talk about what else kind of works. And what kind of rules there are for different things. Okay. Oh, I was wondering what took me off on that whole thing. This did, okay. And then of course you got associativity and distributivity. So for example, 8 times 4 is 8 times 2 times 2, which ends up being just double 16. So they can rearrange parts of the multiplication problem to make it become one of these other things. And in this case, they made it a multiplication by 2 problem, right? Is that cool? Okay, okay. I think I have, yes, cool. I got a couple examples. All right. Multimedia. So guys, here's a pretty damn easy problem. Let's see if you guys agree with me. 5 times 87 times 2. So anyone see, you should be able to do that in your head. What would you do?
5 times 2 is
Yeah, exactly. It's just like when we add, we try to find things that add to be 10, so then we just collect 10s and stuff, right? Here, same kind of idea. We try to find things that multiply to become numbers that are easy to multiply by, and 10 is pretty much the easiest besides 1 and 0, right? So I can use what? I can use what properties? Not, okay, good. I'm glad you said that. Why is this not a distribution problem? And real quick, I've had students do basically this, so this is a mistake. Don't write this. I've had students do something like this and basically do this 5 times 87 times 5 times 2. How many 5s are a factor of the problem? 1. How many 5s have they got now? Do you see the problem? Okay. No. Yeah. So there's only 1 5. Once it multiplies by 2, it's in there already. It is going to multiply by 87. Just it and 2 are going to gang up and multiply on 87. So then I use commutativity and associativity, and I end up with 10 times 87 is 807. Okay. Nothing too amazing. It's very similar to some other stuff. What about, here's a nifty thing. Does anyone have a way to do something like this quickly? We can use a property of multiplication. Besides just, doing the algorithm. So the normal multiplication that we do is an algorithm that needs to be developed with students. So we're going to actually kind of go through some of that, especially with division. Anybody have any ideas? I'll just give you the property. Distributive property. Yes?
You can treat 22 as 20 plus 2.
Yeah! Why is that better automatically? Because 18 times 20 is relatively easy. Isn't that 18 times 10 doubled? You guys kind of with me? So 18 times 20 is just 18 times 2 with a 0 at the end. 360. And 18 times 2 is 36, so then I just get 396. That's much easier to do in your head than visualize 22 over 18 and start carrying shit and doing it, right? You guys kind of with me? Maybe? Okay. In fact, when I have to, it's not the greatest example, it doesn't matter, Jeff. If I have to square something like this,
in my head, which might happen to me more often than you, I understand, but I would do this, right? Because then it would be 900 plus 260s is 120, so 900 plus 120 plus 4. So it'd be 1,024, right? You guys semi with me? And again, the students you're teaching, you might not necessarily do that with, but you could do some lower level shit, and it's built off of these properties. And it helps them, one major thing that I always try to do in my classes is to build from what a student knows to what we're about to do. So I try to find the connection. And obviously in mathematics, it's easier than some other classes to find connections because math is all about building on itself, correct? So I take what they already know and I try to connect it to what we're doing next, right? So it's building that scaffolding. So this kind of thing, when you rewrite it, they know their multiplication by 5s, but not for 87. And then they know the multiplications by 10s, maybe for any number, whatever level the student is at. Okay. Okay, so that's multiplication. Okay. So now let's talk a little bit about division, and then I'll let us out of here. And I'm thinking, just to let you know, I'm thinking our next quiz will be either, I'm pretty sure I'm going to make it next Thursday, because I don't think I'm going to quite make it through section. I want the next quiz to be 3-1 and 3-2. So it's almost definitely going to be next Thursday. Okay. Did I have another one? Oh, true, yeah. Let me do one more of these. What do you guys think about this one? That just wants to be on the floor. 28 times 25. How can you redo that? I wouldn't necessarily do the distribution thing we just did. There's something a little bit more direct you could do. Yeah.
Can you do 20 times 20 and 8 times 5? Okay.
Well, wait a minute. Oh, 20 times what now?
20 times 20 and then 8 times 5.
So 20 times 20, and then 8 times 5, and then add those maybe? Okay. Do you guys all see that 20 is multiplying by 25? And 8 is multiplying by 25. So do you see how that's only a part of what the result should be? So if I rewrote this 20 plus 8 times 25, both of these are multiplied by 25, right? Okay. But don't even think that. There's something more fundamental. What number is... So I have a number 25 in there. What would I multiply that by to make the next step really easy? 25 times 4. So 28 is 7 times 4. And then I could rearrange that using commutativity and associativity. Okay, I like it. Okay. So let me do this. See some of you guys glazing over, and I don't blame you. I've been talking a lot today. I've got something I've done that I'm not going to do ever again, but I want to do it once. So the front side of this is, like an example of what nerdy ass Jeff would do if he was taking this class. I don't know if any of you guys do this. When I was taking a class, I would write the notes in the lecture, and then I would rewrite the notes later, and I would reorganize shit into little things that made sense to me. Right, so very often my teacher would talk about something here, and then later, and I'm sure I do it the same way too. And you're like, well, those two kind of go together. When I rewrite my notes, I'm going to put those together. You guys sort of. So this is just an example of how you could rewrite your notes for section 3.1 through 2, and you're getting a little bit of a preview of the division stuff down there. You guys with me? Okay. On the other side are some problems I want you guys to try real quick.